Hello everyone, I'm from Nanjing University of Aeronautics and Astronautics. I'm honored to have the opportunity to address you on this special occasion. The topic of my paper is a Doppler Disambiguation method for TDM MIMO Radar. My presentation will include 4 parts. The first part, I want to introduce the background of research. The second part shows the proposed method of my paper. And the third part covers the data used in this research, and then introduce the empirical results. Finally, a summary conclusion is given. Well, let's move to the first part of this topic. MIMO radar technology has been receiving considerable attention from automotive radar manufacturers because it can achieve a high angular resolution with relatively small numbers of antennas. The typical frequency band of millimeter wave automotive radar is 76 to 81 GHz. The high frequencies facilitate small enough antennas that can fit behind the bumper of the vehicle. Also, the wide available bandwidth enables a high target range resolution. Additionally, the millimeter wave radar supports different range of configuration. We can deploy several radar in a car for different purposes. The basic transmit signal of FMCW radar is a frequency ramp, also commonly known as a chirp. A chirp is a signal whose frequency varies linearly with time. The signal transmitted by the transmit antenna reflects off one or more objects. The reflected signal is received at one or more receive antennas. FMCW radars transmit a series of such chirps. There are equally spaced chirps in a unit called a frame. The corresponding signal received at the receivers is then converted digitized and then processed to obtain the range and Doppler information. With a MIMO radar, multiple transmitters transmit to the same set of receivers. The signal emanating from multiple transmitters need to be orthogonal. This is mainly implemented with this 4 methods, namely time division multiplexing, frequency division, code division, and Doppler division. The time division is the most intuitive and simple way because each transmitter transmits its own waveform alternatively. There is no overlap between any 2 transmissions, so ideal orthogonality can be obtained. However, TDM schemes results in a reduction in the maximum ambiguous velocity. In order to measure velocity, MFCW radar transmits multiple chirps separated by a time interval, Tc. Phase difference induced by this interval can be used to estimate the velocity of target. The maximum ambiguous can be denoted as this. TDM radars with n antennas enlarge this time interval by n times, so the maximum velocity will decrease by a factor of n. To regain the maximum velocity, several disambiguation techniques have been used previously. The common radar processing is divided into different layers. Each point in the point cloud contains information such as range, radial velocity, and angle of the target. The velocity expansion algorithm based on tracking make full use of the target history information. And this enables the target to be located and the right velocity can be obtained. The velocity expansion algorithm will increase the computational effort of target tracking, and it's difficult to get an accurate angle estimation result. Our work is to provide accurate Doppler information at the target detection layer. CRT can be applied for the disambiguation or the foundation of several subsequent measurements with different time intervals. This method requires a special waveform in combination with fast-slow chirp, and only supports a maximum of 3 times the velocity expansion. HPC technique has been used frequently. This method compensates the velocity induced by phase shift and then selects the correct hypothesis by comparing the peaks of angle FFT results. It works well when the number of transmitters is small. However, as the number of transmitters increases, the complexity of the calculation increases and the accuracy decreases. Well, let's move to the method proposed in this paper. This paper utilizes the phase difference to solve velocity ambiguity by making full use of the phase change information of multiple transmitters and receivers in TDM MIMO radars. This method can obtain the same maximum unambiguous velocity as with the use of a single transmitter. In this process, no extra hardware costs will be needed, and the requirements of calculation will be very simple. A MIMO radar consists of multiple transmitters and multiple receivers, forming a large virtual array. We can obtain the virtual array signal by performing a two-dimensional FFT processing on each transmitter and receive pair. Range FFT receives the objects in range and produces a series of bins. A Doppler FFT is then performed for each range bin of both chirps, and thus a signal at a specific range Doppler bin indicates an object at that range and velocity. Consider an object moving away from radar. For a receiver, the signal from the object must travel an additional distance to reach the next receiver. This distance corresponds to a difference between each two adjacent receivers. It records the angle information of the target. As for transmitters, a similar phase difference can be obtained. Since transmitters transmit alternately in a TDM MIMO radar, an additional phase difference caused by the velocity of object will be introduced. Namely, this distance will result in additional phase change. So this phase difference records both this phase difference records both the angle and the velocity information of the target. The relative velocity of the object can be estimated from the Doppler FFT, and this may be a wrong value. We need to do a Doppler disambiguation for getting right velocity value. This value can be converted into a phase difference, like this. This corresponds to the phase difference of the same transmitter between two adjacent chirps. The figure illustrates this difference for a positive velocity and a negative velocity. Doppler ambiguity occurs when the actual phase change exceeds 118 degrees. This figure illustrates the actual phase change in the case of two transmitters when the Doppler ambiguity occurs. This value can be derived like this for multiple transmitters. Also, this value can be obtained from this derivation. With a combination of this, the number of rotations of phase change can be calculated. Once we get the number of rotations, the true velocity can be obtained from this formula. Then we move to the next part. We validate the method through simulation and measurement data. The data used to validate the method are based on synthetic data generated using the MATLAB Radar toolbox. Here are the parameters of the waveform. We employ an antenna array of 12 transmitters and 8 receivers. As we can see, the maximum unambiguous velocity is quite small. And here is the first experiment. The object directly in front of the radar moves at a velocity varying from -24 to 24 meters per second. The horizontal axis indicates the actual velocity, and the vertical axis represents the measured velocity. And blue points is the FFT result, and red points is the disambiguation result. As can be seen from the picture, we can obtain the right velocity by using this method. And for situation where the target is not directly in front of the radar, this method can also be available. Consider an object moving directly ahead from at the velocity of 10. Maintain a certain angle to the radar. The radial velocity of the object can be obtained by multiplying by cosine theta. Sweeping the angle from -18 degrees to 18 degrees, the velocity is always retrieved correctly. Next is the measurement data. The real data is collected with a commercial cascaded radar from Texas Instruments. This module enables support for up to 12 transmitters and 16 receivers. It is worth noting that 3 transmitters are used to measure pitch angle. On this, we can only perform velocity disambiguation by using 9 transmitters in the horizontal direction. Although the maximum velocity is reduced by a factor of 12, it can still be fully recovered with this method. And this is a self-made RF board. This design discards the pitch angle. It can achieve a high azimuth angle resolution of 0.6 degrees. The environment for data collection is shown in this figure. There are many hills and trees on either side of the road which may cause interference. We collected 15 frames of data. During these frames, the car-informed radar accelerates from static state to 8 meters per second. The left picture indicates that the number of rotations always fall around the correct integer and fluctuates for the reason of noise and clutter. And all velocity values have been successfully resolved. Here comes the conclusion of this research. This method used in my research can obtain the same vaccine unambiguous velocity as with the use of a single transmitter. It does not need any additional conditions and can be used directly to a MIMO radar. It's pretty effective when the number of antennas is large. That's all for my presentation. Thank you.